Okay, guys, so to determine maxima, minima, and saddle point, so this is basically the procedure that we are going to follow. If you've been given your z function, which is written with respect to variable x and y, so clearly this is different from what we did in maximum, minimum, because we just had y written in terms of x. Okay, so here we have z, x, and y. So the first thing that we are going to do basically is determine the partial derivative of z with respect to x and z with respect to y, and then equate them to 0, because for any given stationary point, the gradient is 0. After that, we're going to solve these two equations simultaneously in order for us to get the coordinates of the stationary points. Then after getting the coordinates of the stationary points, we're going to determine the second derivatives. So d2z dx squared, d2z dy squared, and d2z dx dy, then substitute their values in this equation here. Now, the value of this equation is what will help us know if it's a maxima, minima, or a saddle point. Now, so if it's greater than 0, then the stationary point is a saddle point. And if it is less than 0 and d2z dx squared is less than 0, then it is a maxima, maximum point. Then if we have it's less than 0, but d2z dx squared is greater than 0, then it is a minima. So that's the procedure in order for you to determine whether a point is a maxima, minima, or a saddle point. Now I want us to take up an example and see how exactly we go about this particular example. Okay. So find the stationary points of the surface. So find the stationary points of the surface. The surface is z is equal to x cubed minus 6xy plus y cubed. And determine their nature. And determine their nature. Okay, so following the procedure, we'll first of all start by getting the partial derivatives. So I will get partial derivative of z with respect to x, then equate to 0. What's partial derivative of z with respect to x? This is 3x squared minus, when we are differentiating with respect to x, y is treated as a constant. So this is 6y plus, when we're differentiating with respect to x, y is treated as a constant. So this will give us 0. Okay, and equate this to 0. Okay, next, we're going to get the partial derivative of z with respect to y. So partial derivative of z with respect to y, differentiating with respect to y, this is a constant, so the differentiating will give us 0. Differentiating with respect to y, this will give us minus 6x plus 3y squared, and this is also equal to 0. So we are going to solve these two equations simultaneously to get, so call this equation number 1, call this equation number 2. So we are going to solve these two equations simultaneously to get the value of x and y. Now from equation number 1, I can write it as 3x squared is equal to 6y. So, or divide by 6 here, such that y is equal to this. So 3 goes here, so that I have here 2. So y is equal to x squared over 2. Then replace that value in 2. So replacing in 2, what do we have? So I have minus 6x plus 3y squared, but my y is x squared over 2. So square, this is equal to 0. Okay, so what does that give if we simplify? So this is going to give minus 6x plus 3 into x raised to power 4 over 2 squared is 4 is equal to 0. So this is minus 6x plus 3x raised to power 4 over 4. Okay, fine. So this basically gives us, so rearranging this is the same as is equal to 0. I can decide to multiply by 4 all throughout. So I will have minus 24x plus 3x 4 is equal to 0. This is the same as 3x raised to power 4 minus 24x is equal to 0. Okay, so if I factor out x and 3, if I factor out 3x, I will have x cubed minus minus 8 is equal to 0. So this basically gives me 3x is equal to 0. 3x is equal to 0 and x cubed minus 8 is equal to 0. So this gives me x is equal to 0 and x cubed is equal to 8, which gives me x. So the value of x is basically equal to, the value of x is basically equal to 2. So we have these two values of x, then you can be able to get the value of y. Now remember the equation, we say that y is equal to x squared over 2. So since y is equal to x squared over 2, when x is 0, so when x is 0, we will have y being equal to 0 over 2, which basically gives 0. Y is equal to, when x is 2, we will have 2 squared over 2. So y will basically be equal to 4 over 2. So those are the stationary points. We have 0, 0, and we have 0.22. We've already gotten the stationary points, which is the first step. So the next step is to determine the nature. So determining the nature, we need to evaluate the second derivatives. Now come back to z. Z was x cubed minus 6y plus y cubed. So I want to write that again. Here, z is equal to x cubed minus 6xy plus y cubed. So what is the z dx? We already did that, but let's just do it again. 3x squared minus differentiating with respect to x, 6y plus 0. Okay, what is the 2z dx squared? The 2z dx squared basically means, now differentiating this one, again, with respect to x, this will be 6x. Differentiating this other side, we'll have 0. Okay, fine. Now, differentiating with respect to y, what is the z dy? The z dy, differentiating with respect to y, this will be 0. With respect to y, this will be minus 6x plus 3y squared. And then we take that and differentiate again with respect to y. This will be treated as a constant, so it will be 0. Differentiating this, we will have 6y. Then finally, we evaluate the 2z dx dy. So this is basically d dx of dz dy. And this is basically d dx of, what is our dz dy? Dz dy is minus 6x plus 3y squared. So differentiating it now with respect to x, differentiating this with respect to x, we will have minus 1. With respect to x, this will give 0. So this is what we have. Then replacing them into the equation so that now we can be able to determine the nature of our stationary point. The equation is the equation is partial derivative of z with respect to dx dy squared minus partial derivative squared of z with respect to x, and then the 2z dy squared partial. So this is going to help us determine whether it's a maxima, minima, or a saddle point. Now we already know the value for this first one. It is minus 6. So here we have, so let's start with at point 0, 0. At point where x is 0, y is 0. So replacing this, that one is minus 6 squared minus the 2z dx squared. We got the 2z dx squared to be, the 2z dx squared was 6x and the other one was 6y. So this was 6x and the other one was 6y. So at a point where x is 0 and y is 0, this will just give me 0, 0. So 0, 0. So minus 6 squared, that will give me 36. So clearly, since this basically gives me 36 and 36 is obviously greater than 0, then this particular point 0, 0 is obviously a saddle point. Okay, let's look at the next point, which is point 22. So at point 22, what do we have? So we have minus 6 squared minus 6x. So instead of x, let's just write the value of x. The value of x is 2. So minus 2, 6 again multiplied with value of y is also 2. So minus 6 squared, that is 36, minus 12 and 12. So this is the 12 times 12, that will give 144. So clearly getting 144, this is obviously going to give us minus 108, which is obviously less than 0. Which is obviously less than 0. So we determine, in order for us to know the nature, what is the 2z dx squared? The 2z dx squared is 6x, which is basically 6. Our x is 2. So this is 2. And this value here is greater than 0. So since we have it like this, we have this less than 0 and this here greater than 0, then what point is it going to be? This is obviously going to be a minima or minimum point. So basically, guys, that's how we go about determining the stationary points when you're given a function that has been defined with respect to 2 variables. So you get the stationary points and determine their nature like that. Okay. So maybe you take up this example and do it in a similar manner and see if you will get an answer. So example number 2, find the stationary points. So find the stationary points of the surface z is equal to x squared plus y squared, and determine its nature and determine its nature. Okay, so do this one and let's see if you're going to get the answer.